Thanks for joining me, everybody. I'm not going to do video of myself on this one. Just found a fascinating paper that I just want to get out and share with you. It's The Rise, the Fall, the Resilience of Technological Civilization. What Earth's future tells us about the search for alien life. So, we've been searching for signatures of alien life for a while now, and we haven't found any evidence of intelligent life elsewhere in the galaxy. The question, known as the Fermi paradox or the Great Silence, it really has puzzled scientists and the public alike. There's some that argue that intelligent life is rare. Others suggest that technological civilizations, once they arise, are very short lived. They hit a great filter and then they're extinguished. They never get through that. They can collapse due to resource depletion, conflict, systematic instability, or sources beyond their control, supervolcanoes, asteroid or comet impact, things like that. But what if the story is actually just really more complex than that? What if a civilization doesn't simply rise and fall, but they go through cycle of periods of collapse and recovery, sometimes remaining dormant for centuries as they're in the recovery phase? So this study by Blanco, Hawk Misra, and Prolifitis 2026, they did models of the long-term dynamics of Earth's technological civilization, and they explored how collapse and recovery cycles shape our future and influence the detectability of intelligent life across the cosmos, across our galaxy. Here we dive deep into their findings and what they mean for us and our resilience and our search for extraterrestrial technosignatures. So the study, as you can see here, comes up with 10 plausible futures for Earth civilization over the next 1,000 years. Each scenario is basically defined by, let's see, resource regime, scarcity or abundance, governance structure from autocratic to participatory, and then systemic resilience, how well societies recover from collapse. So these scenarios range, as you can see here. S1, Big Brother is watching, centralized authority system under resource stress. You got S2, the Wild West, deregulated, competitive, and fragmented society, a golden age. S3, stable, egalitarian society with abundant resources. S4, living with the land, low impact, cyclical, ecologically constrained society. You have S5, the transhumanism. They're technologically integrated, post biological civilization. You have S6, the sword of Damocles. It's a high tech, high risk system with cascading failure potential. You have S7, the restoration. They've recovered post collapse world with resilience. S8, Ouroboros, oscillatory civilization with cyclical collapse and regrowth. And then the Du Machina, they're an aggressive technologically expansion with instability risk. And then S10, out of Eden, their harmonized coexistence with nature and machines. So, like I said, they range from all kinds of things, authoritarian regimes that are under resource stress to egalitarian post scarcity societies harmonized with nature and technology. Each is mapped to quantitative parameters such as like technological growth, resource depletion, collapse, death, recovery speed, exposure to essential hazards to stimulate cycles of growth, collapse, and recovery. So, some example scenarios: Big Brother is watching. It's a centralized authoritarian system under resource stress, and it's prone to frequent collapse. The Golden Age, like we talked about, and so we just kind of went, I won't go through all that, but they're there. So, the key metrics: how does civilization survive? So, as we come here and we look at what model tracks the four main metrics. Okay, the first is time to first collapse. How long before the first major breakdown of that civilization? And then number two, fraction avoiding collapse. How many runs avoid collapse entirely? 3, duty cycle, the fraction of time a civilization is technologically active and thus detectable. And 4, number of collapse recovery cycles. How often does a civilization collapse and then rebuild? So, what drives collapse and recovery? Well, resource depletion rate, how quickly resources are used up. Here you can see on these images right here, they are the mean trajectories of global technology. Standard deviation is shaded, basically showing mean resource levels are with a standard deviation here. So you can see by the type of civilization they're off on the right, how stable their global tech, how good they are with managing resources. And you can see that some of them are not very good with resources, thus they're going to be more prone for cycles of collapse than recovery. Governance structure. Centralized systems may recover quickly, but are more fragile. Okay, their distributed systems are more resilient, but may recover more slowly. Okay, you can see in this here. We'll go through that in just a minute. And then hazard exposure, eternal risks like pandemics, AI misalignment, nuclear war, supervolcano, comet asteroid impact, all those type of things. So results, patterns of collapse, recovery, and continuity. Here you can see in this graph from the paper, fraction that never collapse, the mean duty cycle, the mean time to first collapse, and then the mean number of collapses by the type of civilization they are. So these will all be posted over on Easy Astronomy if you want to get into it. A link to the papers there. Just a fascinating paper. I'll probably kind of get off the slides here in a little bit and just show you some things in the paper. But so what are the patterns of collapse, recovery, and continuity? So a continuous civilization scenarios like a golden age and out of Eden maintain uninterrupted technological activity with perfect duty cycles and no collapses. That's why if we go back one, you'll see the straight lines here on the top and on the bottom. Their tech is solid, their resource is solid, they're stable. Okay, collapse-prone societies, you can see that on this map right here. Authoritarian or high-risk scenarios suffer early and frequent collapses with long periods of inactivity and low duty cycles. It can be low as the sample is 0.38, 1 being the best, right? 1.0 being the best. So, you can see that with these systems here. You can also see it when we go back to this slide here. And then you have oscillatory regimes. Some societies like Ouroboros experience repeated but non-terminal collapses, maintaining kind of a high duty cycle, 0.87, through robust recovery mechanisms that they have in place. So the importance of recovery and resource management. Here you can see the recovery fraction, depletion rate, recovery delay, and the existential hazard rate for each type of the 9 civilizations that they list here. Sensitivity analysis shows that 2-factor resource depletion rate and recovery fraction are the most powerful levers for civilization resilience. So their small improvements in these areas can dramatically really increase the duty cycle, making civilizations more likely to persist and be detectable. Okay, some real-world examples that they talk about in the paper: seed vaults and biovaults. There's facilities like the Svalbard Global Seed Vault in Colossal Biosciences. The biovault preserves biological diversity, increasing the recovery fraction after a collapse. If we had a major collapse, we have those seeds with their DNA, and we could take those seeds and then begin to repopulate and resupply the food chain and other things like that are needed for a recovery after a collapse. Knowledge repositories, curated recovery kits of essential knowledge can accelerate rebuilding, reducing recovery delay. If you have a collapse and you may have all this information saved, but if it's all based on technology and there's no power to get that, the first thing you're gonna have to do is figure out how to get power back to access that. There's other ways that knowledge is stored so that it can come out and be restored. So then you have a circular economy and renewable energy. Reducing resources depletion through sustainable practices extends the lifespan of civilizations within this study. So, what's the implications for, and here you can see the probability that a technosignature could be observed. We'll talk about that in a minute. So, what's the implications for the search for extraterrestrial intelligence, or SETI? So, maybe from all this, we have to rethink the Drake equation. That famous Drake equation estimates the number of detectable civilizations in the galaxy, with the key term L, capital L, representing the average duration a civilization remains detectable. This study kind of argues that this should be replaced by an effective detectability duration, because the period that a civilization is detectable, it can be just for short periods of time. And so we probably need to adjust that a little bit. So LEF equals duty cycle times observation window. If most civilizations are only intermittently active, going through the periods of collapse and recovery, the probability of detecting them drops dramatically, even if intelligent life, both in the galaxy and the universe, is actually very common. This kind of helps to explain the theory of the Great Silence, right? They're out there, civilizations are out there, intelligent species are out there, and they exist, but their signals rarely overlap with our observation window, okay? They have to be prime, and we have to be prime in our recovery or in our buildup to be able to detect each other. If we're ready to detect, but they've had a collapse, there's no signal coming. Perhaps we reach a point to where we collapse and they've recovered. We're not sending signals, and our signals have just bypassed them, and they never get them. Some technosignatures, like atmospheric chemicals or orbital debris, which you can see here, is this chart shows the probability that technosignatures could be observed, taking into account the duty cycle for each scenario and the lifetime of each technosignature by the types of civilizations they are. So if these persist long after a civilization collapses, they extend the window of detectability. So it's possible we could detect an ancient civilization that has gone through a full collapse. Maybe it's not even there anymore, and maybe we detect it, and like we said, because of the difference in time for those signals to get to us, they've had a full collapse, or they've been obliterated. They're just no longer in existence. However, if most technosignatures are short-lived, and that is the emphasis of this study, the duty cycle remains the key factor here. So actual insights for building a resilient future: probably need to invest in the recovery infrastructure. Something could happen beyond our capability, and our civilization could end up in collapse. So we need to build and maintain repositories of knowledge, biological diversity, and critical technologies to ensure rapid recovery if we go through a collapse. We need to reduce resource depletion, transition to sustainable resource use, and circular economies to delay or prevent a collapse. If we just we have resources and we need to use them. That's part of what we do. We just need to be wise stewards with them and make sure that we're not just consuming until we're depleted and then we end up in a collapse situation. Enhance governance resilience, foster distributed, redundant systems that can withstand shocks and adapt to the changing conditions that are probably going to face us moving forward in our history. And then mitigate existential risks, invest in planetary defense against comet and asteroids, AI safety, and global risk reduction to lower the probability of catastrophic collapse due to things that we can't control. So, the fate of technological civilizations is not just a matter of luck, it's a matter of design. By understanding and actively managing the dynamics of a collapse and recovery, humanity can increase our chances of long-term survival and perhaps becoming one of the rare civilizations whose signals echoes across the galaxy and are picked up by another civilization in another world that does the same thing. For those interested in the technical details or running their own simulations, the code used in the study is available, and I have a link on Easy Astronomy for that, and then a link to the paper. The paper is absolutely fascinating, okay? Just to pop out of this really quick and just pop to the paper really quick here. You can see it: projections of Earth's technosphere, civilization collapse recovery, dynamics, and detectability. And they just go through some wonderful things in the paper here. They talk about how the apparent contradiction of the Drake equation, that whether there's intelligent life that exists elsewhere, and if so, why haven't we detected them? It's often referred to as the Fermi paradox or the Great Silence. It raises the question of why in a galaxy billions of years old, over 13 billion years old, we observe no clear signs or signals of advanced extraterrestrial life. Many solutions have kind of been proposed to explain that. They explain that in the paper here. One class of explanation suggests that, as they say here, intelligent life is intrinsically rare, perhaps requiring an improbable convergence of planetary, chemical, or biological conditions to happen. And I just shared a paper about that recently about that. And they just go through it. The read is fascinating. I just invite you to take a look at it, to enjoy it, to really get through it. And anyway, like I said, just fascinating. I probably haven't done it justice, but I invite you to go ahead and read it and maybe run your own simulations if you're that gifted. Thanks for joining me. Hope you have clear skies, and we'll talk to you soon.